How long is this video going to be? I have no idea, but we're going to do it. This is the Jiggle Pendulum. This is one of my favorites. So let me describe the situation. I'll talk about the Lagrangian, and then we're just going to do it. We're going to get an equation of motion, and then we're going to build this model in Python, and I don't care how long this takes. We're just going to do it. Okay, so hold on. So this is we can call it a stick. It's a massless stick with a mass on the end of it. So the stick has a length L and there's a mass M, and it's connected to this cart up top. And the cart jiggles back and forth. So it just oscillates back and forth with some position A cosine omega t, where A is the amplitude, omega is the angular frequency of oscillation, and that's that. So how do we model this? And you could this is one of those great ones that you could think, what the heck, how would you do this with Newtonian mechanics? It's not so trivial because you couldn't calculate the tension in there and model everything. It's pretty tough. But with Lagrangian, it's not so bad because I can model the motion of this by picking a generalized coordinate, and which is going to be, in this case, the angle from the vertical theta. But theta doesn't tell me the exact location of this. Tells me the location of this with respect to that, and that's moving back and forth. Okay. So, but if I pick a coordinate like that, and this is just a 1 degree freedom problem, I don't really need any other coordinates. Yes, this moves back and forth, but that's according to time, not according to the position, the variable position right here. So, what was I saying? Position, using Lagrange. So if I get the kinetic energy and the potential energy in terms of this angle theta, then I can use the Euler-Lagrange equation to find an expression for the equation of motion. And then I'll solve that numerically with Python. I think I'm skipping a step, but I'm going to go ahead and jump into it. Yes, it's 1 degree of freedom. That's a pretty good choice to pick. But now I want to get the kinetic energy. So kinetic energy is 1/2 m x dot squared plus y dot squared. It's easy to write in Cartesian coordinates. It's not easy to write right there. So what I'm going to do is get the x and y position of this. So let's call this x1. That's the location of the top down here. And I'll call this x. So if I say x, the x location of this is going to be the location of this, x1, plus this distance. So that's a right triangle. So that's going to be plus L sine theta. So that's going to be, if I add this in here, A cosine omega t plus L sine theta. That's my x. And now for y, it's just going to be this coordinate down here. I'm going to call this y equals 0, so that's going to be negative. So y is negative L cosine theta down there. So it doesn't matter where that is, the y is not, it only depends on that angle theta. Okay, and I can do the same thing for the potential. The potential is just going to be mgy, which I have y, so that's pretty easy. But now I need to take the derivatives of this. So let's start with that. X dot is going to be equal to, okay, I'm going to start over here. What's the derivative of A cosine omega t? And I'm, just so you know, dot, I should say this, x dot is dx dt. Y dot is dy dt. If you haven't seen that notation before, it just makes things a little bit easier. Okay, so I'm up here. The derivative of this. So A is a constant, omega is a constant, but I do have a t right there. So the derivative of cosine omega t is negative sine omega t. So I get negative A sine omega t. But then I have to take the derivative of the inside, and the derivative of that's just going to be omega. So I get negative A sine omega t. Now I need to take the derivative of this with respect to time, and I get L is a constant. So the derivative of sine is cosine, so I get plus L. You notice I leave a space here because I've made this mistake before. But then I have to take the derivative of theta with respect to time, and that's theta dot. Now let's do the same. Now let's do the same thing for y. Y dot is going to be pretty easy. The derivative of cosine is negative sine, so I get L theta dot sine theta. Now I need to square x dot, square y dot, add them together, so I get x dot squared. I get this term times itself, so it's going to be a squared omega squared sine squared omega t. Now I'm going to get this times that twice, right? Because I have two of these things. So I get minus 2a omega L theta dot, and then I have cosine theta, and then sine omega t. And then I get this squared. So it's going to be plus L squared theta dot squared cosine squared theta. Now y dot's pretty easy. Y dot squared is just going to be equal to L squared theta dot squared sine squared theta. So now I can get x dot squared plus y dot squared. That's going to be equal to this term, a squared omega squared sine squared omega t, this term, minus 2a omega L theta dot cosine theta sine omega t. And now this term, I'm going to factor out the L squared theta dot squared. So I'm going to say plus L squared theta dot squared times cosine squared theta plus sine squared theta. And you see what's happening there. Cosine squared plus sine squared is 1. So there's my, now all I have to do is multiply that by 1/2 m, and I can get my Lagrangian. So let's write down the Lagrangian. Next page, please. Okay. So L is going to be 1/2 m times this, a squared omega squared sine squared omega t, minus, now I have a 1/2 times 2, so I just get m a omega L theta dot cosine theta sine omega t. And then I get plus 1/2 m L squared theta dot squared. Now I have the potential, so I have minus the potential, and I already said the potential was mgy, but why is that? So I'm actually going to get plus mgl cosine theta. Got the Lagrangian, done with that sheet right there. Okay. Now I only have one variable, so it's not so bad. So let's take we got to find the partial of L with respect to theta, the partial of L with respect to theta dot, and then take the derivative of that. So partial of L with respect to theta. Let's do that first. I'm looking for thetas. Theta, 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 theta. There's one right there. So this is just a constant when I take the partial with respect to theta, so it's 0. This has a theta term in it. I don't have to worry about theta dots. I'm just doing theta. So I have the derivative of cosine theta is going to be negative sine theta. So I get that is going to be plus. I get m a omega L theta dot sine theta sine omega t. That's it. Now I need, here's another theta over here. Yeah. So the derivative of that's going to be minus mgl sine theta. Now we can go on to the partial of L with respect to theta dot. Okay, I'm looking for theta dot terms. Nope. Here's one. And that's pretty easy, right? If I take the partial of this with respect to theta dot, I just get all that stuff without the theta. So I get minus m a minus the theta without the theta dot. A omega L cosine theta sine omega t. That's an omega. Then here's another theta dot. So if I take the derivative of this with respect to theta dot, the partial with respect to theta dot, I get the 2 comes down front, and I get 2 over 2 m L squared theta dot. So it's going to be plus m L squared theta dot. Now I can take the derivative of this with respect to time. The derivative with respect to time of the partial of L with respect to theta dot. Now it really matters that every term that changes with L I have to take into account. So these are all constants, but then I have a cosine theta. So I'm going to take the derivative of cosine theta with respect to time, and that's going to be negative sine theta. And then I take the derivative of the inside. So I get m a omega L theta dot sine theta sine omega t. Now I have to take the derivative of this term with respect to t. The derivative of sine omega t is going to be cosine omega t times the derivative of the inside, so it's going to be omega. So I get minus m a. I had omega already there. I'm going to get an omega squared L cosine theta cosine omega t. Now this term's pretty easy. The only term that depends on time is theta dot. So the derivative of theta dot with respect to time is going to be theta double dot. So it's going to be m L squared theta double dot. Whew, okay, so we got it. Now we can put this equal to that, and let's do that. I get m a omega L theta dot. See, you know, I just want to point out, not skipping steps is very useful here because there's a lot of stuff going on, and now I stopped. I'm probably going to make a mistake because of that, but sine omega t minus m a, that's an m, omega squared L cosine theta cosine omega t plus m L squared theta double dot equals this, m a omega L theta dot sine theta sine omega t minus mgl sine theta. I ran out of room. Okay, so the masses cancel. But actually before that, look at this. m a omega L theta dot sine theta sine omega t. It's right over there too. These terms cancel. Yay. Let's move this term to the other side and divide by m, right? I can divide every term by m. That's gone. So now I get L squared theta double dot equals minus GL sine theta. And then I'm going to add this term to both sides plus a omega squared L cosine theta cosine omega t. That's it. Now I'm going to divide both sides by L squared. And I get theta double dot equals negative G over L sine theta plus A over L omega squared cosine theta cosine omega t. Is that right? I don't know. Well, let's see. How about this? What if the frequency of the jiggle goes to 0? That means this is just stationary. If that's stationary, this becomes a normal plane pendulum. And I actually know the from a previous problem, theta double dot for a normal pendulum is negative G over L sine theta. So that's good. The other thing that we can check is the units, right? This has units of radians per second squared. This has to have units of radians per second squared, which it does, right? Because I have meters per second squared divided by meters. So I get 1 over second squared. That has no units, so that's good. This is meters over meters, 1 over second squared, no units, so that's good. So I think there's nothing to say it's wrong, right? So let's just say it's right. But we're going to use that. So now, but how would I find the motion of this mass using that? That's a non-trivial differential equation. I mean, I'm sure you can solve it, but I don't want to do that. I want to do it numerically. And it's not cheating to do it numerically, okay? It's not cheating. It's not. It's just the way we do things. So if I have, break this into small time steps. I'm going to pick delta t equals 0.001 seconds. So during that time, I can assume that theta double dot's constant. If theta double dot's constant, I can write theta double dot equals delta theta dot over delta t. That's the definition of, this is really just the same as saying A equals delta v over delta t, right? The definition of acceleration. Except now I'm dealing with the angular velocity. So it's the second derivative is the derivative of the first derivative, but I'm writing it not as an infinitesimal derivative, but as a finite time step. So now I can write this as theta double dot equals delta theta dot, so it's going to be theta 2 dot minus theta 1 dot over delta t. So theta 2 dot is the angular velocity at the end of the time interval, and theta 1 dot is the angular velocity at the beginning of the time interval. So with this, I can multiply both sides by delta t, and I get theta 2 dot equals, well, and I add theta 1 dot. Theta 1 dot plus theta double dot delta t. So this says that if I know theta double dot, I can go over here, and I know where it's the initial angular velocity. I can find the angular velocity at the end of that time interval. Okay. And then I could do it for the next time interval, next, and so forth. But the theta double dot also depends on theta, right? There's a theta in that term. So I need to find theta also. So let's do the same thing. Let's say theta dot equals delta theta over delta t, which is not true, okay? But we're just pretending like it is. So I can write that as theta 2 minus theta 1 over delta t. And I can solve again. I get theta 2 equals theta 1 plus theta dot delta t. Now I'm going to write down here theta 2 dot, right? Because if I do this in order, I will calculate theta double dot based on this equation. Okay, so I know my initial theta, I know my initial theta dot, even though theta dot's not even in there. And then I can plug that in to here and solve for the angular velocity at the end of the time interval. Then I can use that angular velocity to find the angular position at the end of the time interval. And then I go do it again. Do I have to write out do it again? No, I don't, but I want to. And you just keep repeating that over and over and over again. If I want to model this for 1 second, I'd have to do it 1,000 times. And I don't want to do that. Do you want to do that? No. But Python doesn't mind doing that. And that's what I'm going to use. I'm going to use Python. You can use Java. You can use C++. You can use Fortran. It doesn't matter. But the idea, you can use humans. You can actually do it on paper. But the idea of a numerical calculation is to break this into small steps and make these approximations over that small steps and then just let it run out from there. And so I'm going to do that. We're going to move over to Python. I'm not only going to calculate this, I'm going to model it with VPython too so we can see what it looks like. Okay, let's jump over there. I'll meet you over there. Okay, so here we are. I'm using Trinket.io. This is an online place where you can type in some Python stuff. And so I've already started a little bit. I've already put in some of my constants here. But the rest of them is going to build from scratch. So let's get to it. So one of the things we want to do is to actually make a visual model of this. I'm going to make a cart, and I'm going to make a ball and a string. I'm going to make all those things, and they're all going to move. But I already have the length of the string, 20 centimeters. Gravitational field is 9.8. This is the amplitude of the oscillation, the angular frequency of the top, and time 0. And then the initial position and the initial velocity. I put that at 15 degrees, and there's no really reason why. So let's first make the car. Let's call this the jiggle. Is that okay? The jiggle. I don't know. That's kind of cool. It's an object of type box. And I'm going to put it at, where should I put it? Let's see, if I put it at the origin, it might not look great. I'm going to put it at position is going to be vector. I guess I could go ahead and put a times cosine omega times t. That would work, right? That's the position. And then the y value is going to be, let's say, 10 centimeters up. So 0.1. And that way I can put the other thing will be down, and then the z coordinate will be 0. Now the other component of a box in VPython, this is VPython in Trinket.io with GlowScript. It's all the same thing really. Is the size. So the size is a vector with the length, width, and height vector. So the length will be, let's see, so if it's going to move back and forth, if it's 20 centimeters, say, let's say 2 centimeters, 0.02. I don't know. That might not work. The height, let's put it as a box. 0.03, and then the width, 0.02. And I'm going to leave it at no color and just leave it as gray. Let's run this because I always like to run things in case I make a mistake at the very beginning. And there's my, see, that does look weird. The size is, let's put this at 3 and that at 2. Yeah. I don't know why I did that. I mean, it worked, right? Yeah, let's keep it like that. Okay. Now the next thing I can do is make the mass. So the mass is going to be a sphere. Its position is going to be the position of the jiggle. So jiggle.pos minus, or let's say plus the vector. Now I'm going to say the x component is going to be L times cosine theta. And I have theta and I have L, right? So that's, oh no, wait, this is sine. I'm sorry. And then the y component is going to be equal to negative L times cosine theta. And then 0. And that's the position. The size of it, I need to give it the size. So let's say the radius is going to be 0.01, and let's make it yellow. Yellow shows up really good with the black background. Color equals color.yellow. Also, let's turn on the trail. So let's say make trail equals true. Let's run that. That's surprising because I thought it would be, oh, it is 0. I did put it at 0. Does that look okay? I think that looks pretty good. Okay, now I just need to make the string, I don't know if it's a string or a stick. Let's call it a stick. Stick equals a cylinder. So the position of this is going to be, jiggle.pos. So in Python, a cylinder has three properties really. First is the vector position of one end of that cylinder. The next is a vector from the beginning to the end. We call that the axis. And then third is the radius of that string. So let's say the axis is going to be from the box to the mouse. So it's just going to be mass.pos minus jiggle.pos. I really like saying jiggle. It makes me it's kind of fun. The radius is should be smaller. So that was, what was the radius of that sphere? 0, 1. So radius is going to be 0.005. Let's just leave it as gray. Let's see what happens. That's a little thick. Let's make that 3. I mean, it doesn't matter for the physics, but it does matter for me, right? It's not just physics, it's art. A little bit thinner. Okay, yes, awesome. Okay, so we have everything right there. Now we just need to, I have the time, I have dt, so all I need to do is to make a loop where I can do these calculations. So I'm going to run it for 10 seconds. I just picked 10 for no reason. So while t is less than 10, the next thing I need to do is the statement rate 1,000. So rate 1,000 says don't do more than 1,000 calculations a second. Since I have a time step of 0.001 second, 1,000 times per second would be real time. So this should take 10 seconds to run. The next thing I'm going to do is calculate theta double dot. Now I'm just going to type in this equation. I can call it, say, theta d dot. That's my double dot. See, that's what I'm going to call it. And all I'm doing is typing in the equation I had from before. Negative g, let's write it the same, negative g over L times sine theta. And then I'm going to have plus a over L. I'm just typing this in, times omega squared times, squared in Python, raised to the power is star star, if you don't know that. Cosine omega times t, times type, I'm looking at the screen, times t times cosine theta. I think that, was that it? Yep. Let me just check my equation right here. That's it. Okay, so that's theta double dot. Now I can use that to calculate theta dot. So I already have a starting theta dot up here. See, theta dot equals 0. So I'm going to go down here and update that and give the new theta dot. So theta dot equals theta dot plus theta double dot times dt. So in Python, this is not an algebraic equal sign. It's a make equal to sign. So this is the theta dot at the beginning of the time interval, and then it just updates that value to make it the new one. So it's really nice. You don't have to have all those indices. And now I can do the same thing with theta. Theta equals theta plus theta dot, and this is times dt. This is the Euler method of numerical calculations. There are more complicated numerical recipes. There's the Runge-Kutta fourth order Runge-Kutta, which is a little bit more complicated, but I think this one works fine. I'll link that video on how that works down below, but I like to use this one just because it's the simplest. Now I can update time, t equals t plus dt. But now I've calculated theta, but now I need to move stuff, right? So I need to move the box or the jiggle. I need to move the mass. I need to move the stick. So I'm going to say jiggle.pos equals, I'm just going to copy this up here. There. That's all I had to do, right? Because t changes. So this is going to move that position back and forth automatically. Now for the mass, I'm going to say mass equals, watch this, position equals the same thing, but it's a new value. So mass.pos, I'm sorry, mass.pos equals, and I don't need the POS in there twice. That was just a copy error. So so it's going to be the position of the jiggle plus, again, the vector L times sine theta. But theta has updated, and I missed a parenthesis. I didn't copy the whole thing. Oh, yeah. That's it looked weird because of this. Okay, there's the rest of it. There we go. Okay. So that's going to update the position of the mass. And then I need to update the stick. So stick.pos. POS equals mass.pos. And stick.axis, because I need to turn it too, equals jiggle.pos. Mass, fine, it's going to be the mass.pos minus jiggle.pos. Does that work? Is that it? Let's find out. And I don't know. I'm going to be as surprised as you are because, you know, you type all that stuff and you might make a mistake. So let's just run it and see what happens. I mean, I'm kind of impressed with myself. I don't see anything wrong, right? And it isn't 3D, but not that it really matters. Okay, let's do this. So if I want to test, right? So I can make it just a normal pendulum. If I put omega at 0, and it should run just like a normal pendulum. I mean, that looks right. It's hard to tell. We could make a graph of this. I'm not going to do that. I'll let you guys do that. I'll include a link for graphing down below. What if I do this? What if I say print square root of G over L? So G over L is the fundamental frequency for a pendulum. And so the thing is, if I use that frequency for my jiggle, then it should be like a resonant state. It should increase the amplitude of oscillation. So let's just run this and get that value. I don't even have to print it. So 7. Okay, so let's go up here and say omega equals 7. And I'm going to put theta at 0. So I'll start it at the origin. And let's just run it. And I don't need to print anymore, so I won't take that out. And let's run this. Yeah, look at that. Okay, I'm kind of happy with that. That looks pretty cool. I mean, I'm not 100% sure it's right, but it doesn't look wrong, right? That's what I would think it would do. If I change this back to something a little bit less, 6.9, it should still make it bigger, just not as big. Awesome. Actually, let's do this. One more thing. Change this back to 7. Change the amplitude of oscillation even smaller. Will it start getting bigger even with the super small jiggle? Yeah. All right. I like that. Look at that. I'm excited. Okay. Okay, so I mean, I'm going to give you this code down below. You can play with it. You can make a graph of it. You could try different things. I have right in my mind 80 different things you could possibly try, but I want you to try it and play with it. Have fun with it. Do the Lagrangian. Do some more physics, and I will talk to you later.